Hello everyone, I am Mohammad Rahatul Hassan Rahat, and here is our presentation topic is irregular sequence counter. So, what is counter? Counters are one of the most useful parts of a digital system. A counter is a sequential circuit that holds the ability to count the number of clock pulses provided at its input. Counters in digital circuits are devices used for counting. These are sequential circuits made of flip-flops. There are two broad categories of counters. Those are asynchronous counter and synchronous counter. So here is the asynchronous counter. Asynchronous counters are those counters which do not operate in simultaneous clocking. In asynchronous counter, only the first flip-flop is externally clocked using clock pulse while the clock inputs for the successive flip-flops will be the output from a previous flip-flop. That means that only a single clock pulse is not driving all the flip-flops in the arrangement of the counter. Asynchronous counters are also known as ripple counters and are formed by the successive combination of trailing edge triggered flip-flops. It is called so because the data ripples between the output of one flip-flop to the input to the next. Asynchronous counters are those whose output is free from the clock signal. Flip-flops are not connected to a common clock. Flip-flops do not change their state at the same time. Some common asynchronous counters are 2-bit binary counters, 3-bit binary counters, and 4-bit binary counters. Asynchronous modules 12 counters.
Assalamu alaikum, sir. My name is Al-Jobair Ibn ATAUR, and now I am discuss about synchronous counter and irregular sequence counter. So first of all, sequence counter. A sequence counter is a contrast to an asynchronous counter is one whose output bit change. The only way we can build such an a counter circuit from JK flip-flops and in the connect all the clock inputs together so that the flip-flop receive the exact same clock pulse and the same time. Synchronous counter are called sometimes parallel counter is the fed parallel of all flip-flop. JK flip-flop is obviously used and the design is a complex compared the asynchronous counter. The synchronous counter are easier to design than asynchronous counter. They are called synchronous counter because the clock input the flip-flops are all the clock together at the same times with the same clock signal, and due to this common clock the pulse all output states switch or change simultaneously. Common synchronous counter is like 2-bit binary counter, 3-bit binary counter, and 4-bit binary counter. Synchronous BCD decade counter, up-down synchronous counter, and irregular sequence counter. So now irregular sequence counter. Irregular sequence counter is like um, to design an irregular sequence counter, we need to first understand the concept of the state machine. There is a two type of state machine: Moore state machine and the Mealy state machine. The Moore state machine is the finite state machine whose the current output values are determined only by its current state, and this is the contrast of the Mealy machine whose output values is determined both by this current state by the values of its input. Like a combinational logic and a memory, the combinational logic goes into memory and memory goes into the combinational logic. It is depend the state, and then the output is began. The Mealy machine is defined as a sequence network whose output is the function of both the present state in the input of the network. The state diagram for the Mealy machine is the output association to the transaction between state as shown as the state diagram. Like combinational logic and memory, where input is the input to the go combinational logic, then to the go memory, and then memory sudden become the present state to combinational logic, and combinational logic state to the output. The state machine have the finite number of the state machine go about in the prescribed manner. A state diagram is a diagram which is show processive of state. The order of sequence diagram is described to the help of this state diagram. So thank you so much, sir. Assalamu alaikum.
my group mate for explaining what is irregular sequence counter. Now I'm gonna explain how to design a irregular sequence counter. We need to follow 5 steps to do the design of irregular sequence counter. In the step 1, we have to check how many bits required in design sequence counter. Then we have to develop a state diagram. In the step 2, we have to develop a next state table by using the state diagram, which is in step 1. And the step 3, we have to create a flip-flop transition table. Then we have to go to step 4, where we have to derive the logical requirements by using K-map. And the last step, the step 5, we have to implement a counter to produce the specific sequence state. Now I'm gonna explain how to develop a state diagram in the next slide. In this page, I'm gonna explain how to develop a state diagram. To develop a state diagram, we have to maintain a one given sequence numbers. So here we choose the given sequence number is 0, 1, 3, and 5. So here we can see the biggest then the highest count is the 7. So we need to use 3-bit binary numbers. So we have to convert the sequence numbers into binary numbers. Then we have to use those binary numbers into different states. Then we'll design those from 0 to 7 in sequence. Then we will find this diagram. Now my next group mate will explain the next state table from this diagram. Thank you.
Assalamualaikum, my name is FAIYAZ. I'm going to talk about irregular sequence counter design, step 2 and step 3. Step 2 is to draw the next state table. To draw the next state table, we need the help of a state diagram. When the present state is 0, 0, 0, with the help of the arrow sign, we can see that the next state is 0, 0, 1. When the present state is, we are at 0, 0, 1, the next state will be 0, 1, 1. When the present state is 0, 1, 1, the next state will be 1, 0, 1. When the present state is 1, 0, 1, the next state will be 1, 1, 1. When the present state is 1, 1, 1, the next state will be 0, 0, 0. We will go back to the first state. We will put these values in here, the next state table. The next step 3 is transition table. From the table we can see that when the present state of Q is 0 and the next state of Q is 0, the value of J is 0 and the value of K is don't care. When the present state of Q is 0 and the next state of Q is 1, the value of J is 1, the value of K is don't care. When the present state of Q is 1 and the next state of Q is 0, the value of J is don't care, the value of K is 1. When the present state of Q is 1 and the next state of Q is 1, the value of J is don't care and the value of K is 0. For each state Q0, Q1, Q2, we will have J and K value separately. For Q0 we will get J0, K0. For Q1 we will get J1, K1. For Q2 we will get J2, K2. When the present state of Q is 0 and the next state is 1, from the transition table we can see that the value of J0 is 1 and the value of K0 is don't care. When the value present state of Q0 is 1 and the next state of Q0 is 1, from the transition table we can see that the value of J0 will be don't care and the value of K0 will be 0. Like that we will have to draw find out the every value of J0, K0, J1, K1, J2, K2 to draw the Carnot map. Thank you.
Assalamualaikum, I'm SANJIDA. I'm from CSC department. So from flip-flops transition table we get this table, present state, next state and next states. So we are going to use Kirchhoff map to derive these logic requirements. By using Kirchhoff map we have to solve it, and by solving it we get some logics. The logics are J not equal 1, then J not equal 1, J1 equal K not, Q not, J2 equal Q1, then k naught equal q2 q1, and k1 equal 1, and k2 equal q1. Then in next slide we are going to implement those logics in the circuits. Those came up those logics we get from came up solving K-map. Those values are we going to connect and make this circuit diagram. So in the end I have to say that every step is important, and we have to every step is related to one another, so we have to careful about the whole process, and that's it. Thank you, sir, and thank you everyone whoever watching this. Thank you.